In this preliminary section, we're going to be revisiting some concepts that we've seen in earlier courses, and we're going to establish some terminologies and lay down some basic notations that we shall be needing and using throughout the course. Let's start with the following definition. What is a set, a mathematical set? Well, a set is a collection of objects, each of which is called a member or an element of the set. Think about a set as a basket that contains objects, and each of those objects is referred to as a member or an element of that basket, of that set. There are many ways to represent sets. One way is to write curly brackets, and list the elements of that set inside those curly brackets. And the resultant writing can be read as follows: the set of, or the set containing. For example, if I write the following, so this means I'm talking about a set, and let's put objects inside. Let's say I have these three objects, A, B, C. So how would you read this writing? This is the set consisting of the objects A, B, and C. Okay, let's take more examples. Let's take a look at this first example here. The set of natural numbers. So what are natural numbers again? Natural numbers are positive integers. Okay, so natural numbers is another phrase to say positive integers. So the set of all natural numbers can be written as follows: curly brackets for set, and you're gonna list all of them here. Obviously we cannot because we have infinitely many. So what we're gonna do is we're gonna write 1, 2, 3, dot, 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 and the presence of the dot, dot, dot is I'm preserving the pattern that exists already, which is understood, right? What's the pattern here? The pattern is just add 1 to the preceding element to obtain the next one, and this keeps going forever. Okay, so that's the presence. That's what this means, the 3 dots, the ellipses. Okay, instead of writing this whole thing, people found a symbol representing that, and this symbol is this boldface N. Okay, so what is this symbol again? This means the set consisting of all natural numbers. You can read this again as boldface N. Next, the set of integers, it's universally denoted by Z. By the way, all these symbols that you're going to see here, these are universal symbols, which means if you open any math book and you see them, they mean exactly how they are defined here. Okay, so the boldface Z, which is denoting the set of all integers, is the set. So it can be written as curly brackets, and you list all the integers. Since the integers, you have infinitely many integers, again we're gonna adopt the same thing. We're gonna have dots to represent the pattern, that exists forever. So here you have double infinite because this keeps going on the positive side exactly as it used to for natural numbers, and also it keeps going on the negative side, correct? So this double infinite set can be written as curly brackets dot 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 minus 3 minus 2 minus 1. Again, the dot 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 means the pattern keeps going this way forever, which is just chipping away 1 unit from the succeeding one to get the preceding one, and all the way to the positive side, and that pattern keeps going again. Okay. Moving on to the set of rational numbers. So what's a rational number again? Well, a rational number is any number that looks like a quotient between two integers. So it's a fraction where the guy upstairs and the guy downstairs, each one of them is an integer. Okay, so each one of them is an integer. Obviously the guy downstairs cannot be 0 because we don't know how to divide by 0. So a rational number is any number that looks like this, and the set of all rational numbers is denoted by boldface Q. Again, this notation is universal. But in contrast with examples 1 and 2 above, we cannot enumerate the elements, all the rational numbers. There's no pattern among the rational numbers like we used to have for natural numbers and integers, right? Remember, the pattern was you just add 1 to the preceding one to get the next one in both cases. For rational numbers, there's no pattern. So because of that, we cannot follow suit here. However, we can give the description like I just gave here, right, in purple. So it's a set consisting of objects. Each object looks like a quotient, A over B. So A represents the asterisk and B represents the star. And the membership to the set is that A and B, so the guys upstairs and downstairs, A and B here, are both in Z. And what's Z again? It's the set of integers. So we're saying the same thing. So A and B should be integers with the property that B cannot be 0. As we said, downstairs cannot be 0 because we don't know how to divide by 0. Okay. So so instead of writing like we used to in examples 1 and 2, instead of enumerating the elements because we were able to, over here we cannot. We can still establish a good writing for the set by just writing the membership to the set. So there are two memberships here. Each object should look like a quotient, and the participants in this quotients, namely the guy upstairs and downstairs, should be in Z, so they should be integers, and the guy downstairs, so B, cannot be 0, right? So this is another writing, or this is another way to represent a set, and this way is referred to as set builder notation. Okay, so this writing is called set builder notation. Okay, all right. And the last part, it's the set of all real numbers. So all real numbers. The set is denoted by boldface R, and is simply, I'm gonna just give the description of the objects inside. So I'm gonna put my typical curly brackets to denote the set, and it consists of, this set is consisting of all numbers, all real numbers that correspond to points on the number line. So any point on the number line, remember the number line, any point on the number line, you name it, is an element in this boldface R set, in the set of all real numbers. Okay, for example, square root of 2 is there. I don't know, negative pi is there, and so on. Okay, all right. Next, this next definition is more of a notation. It's about the following. If you have a set capital A and little x is an object inside A, it's an element inside A, we write this symbol here and we read it as follows. X is an element, so this euro-like symbol here is an element of A, or a member in A. So A is the basket, that symbol means element, and X is the object inside the basket A. Okay, so here again, this pink symbol means X is an element of A. And you write this blue symbol, it looks close to it, but with this bar, and as you might guess, like different, right? So this fails. If this fails, it means that X is not an element of A. Okay, so one more time, this symbol means element, On the left side sits the object. On the right side of this symbol sits the set. And if you negate this, which means you put a bar here, it means it's fading. It's not an element. Okay. Let's take a look at the following. Let's take a look at the first one, which is this guy. How would you read this? You can read it as 5, right? X is 5, and the set is boldface n, which is, again, what does it mean, boldface n? Boldface n is the set of natural numbers. And what are the objects in the in the set of natural numbers? They are the positive integers. So what this example is saying is that 5 is a natural number. 5 is a member of n. Is it true? Yeah, 5 is a positive integer. So this is correct. Okay. The next one, this one. 0 is not a member of n. 0 is not an element in n. That's correct, because the set of natural numbers contains only positive integers, and 0 is not positive. Okay, so 0 is not an element in n. This is correct. Next, this one. -2 is an element of z. Is this correct? What's z again? Boldface z is the set of all integers. Boldface z is the set of all integers, so this whole thing. -2 is there, you see it? It's right there. So -2 is an element in z. So is this correct? Yes, that's correct. How about that one here? 3/4 is not an element in z. Yeah, that's right. 3/4 is 0.75 is a quarter, as a 3/4. Certainly is not an element in z, because z is the set of all integers. So 0.75 or 3/4 is not an integer. So this green thing again is correct. How about this? 3/4 is in Q. What's Q again? Q is the set of all rational numbers. And what's a rational number? Is any number that looks like a quotient, where the guy upstairs and downstairs, both of them are in z, are integers, and the guy downstairs is not 0. So let's check this. 3/4. 3/4. Is 3/4 in this set? Does it verify the two conditions, the two memberships of the set? Yeah, 3 is the A and 4 is the B. And 3, so the A, the 3, and the 4 are in Z. They are integers. Right? The 3 and the 4 are integers. They are here, right? And obviously 4, the B, is not 0. So this condition is verified, and this membership is also verified. So 3/4 verifies the memberships to the set Q, and as such, it has to be part of it. Okay, so this green thing also is correct. Very good. Now here's a question to you, and we'll discuss it during our class time. So is it correct or false? This writing, 7 is in Q. 7 is in Q. Is it correct or wrong? Just think about it. Okay. What does it take for an element to be in Q? It has to be written as a quotient. It has to be, what is it? It has to be written as a quotient where the guys upstairs and downstairs are integers and the guy downstairs is not 0. Can you write 7 as a quotient where the guy upstairs and downstairs are integers and the guy downstairs is not 0? Think about it. Alright, moving on. The next definition is about intervals. Let's give ourselves a context. Let's take two numbers, A and B, and look at the writing here. What am I saying here? Let A comma B, this symbol R. This means let A and B be elements of R, right? And boldface R means, boldface R, let me take you back here. Boldface R stands for the set of all real numbers. So how would you read this using just pure English here? Let A and B be two real numbers, right? This is what this thing is saying, such that A is smaller than B. Okay. So one more time, let A and B be two real numbers, since they are real numbers, and let's say they're not the same, so one has to be smaller than the other. So let's say that A is the smaller. We define the following intervals. This interval here, this means nothing except once you read what comes after the equality. You see here I'm putting colon before equality, meaning I'm defining this object. This is like a picture. Whatever this picture is, it means the following. Okay. What does it mean? What does this thing means? It means the collection, the set of all real numbers, right? Of all real numbers, such that those real numbers should be simultaneously bigger than or equal to A and smaller than or equal to B. Okay? So let's take a moment to actually write this whole thing. Let's actually take a moment to write this whole thing using pure English so that you get used to it. This is set builder notation again. X is a generic element inside the set. That generic element, any element in this set AB here should be a real number, but not any real number is invited, just those which are between A and B. Okay, so this means it's the set consisting of all real numbers X with the property that X is at least A and is at most B, right? This is what this bubble means. It's a set because of the presence of the curly brackets, and it consists of objects that they are represented as X. They are real numbers. You see here X is in R, so they are real numbers, right? This is this part. And there is another membership. The membership is these objects X cannot be anything. They have to be numbers between A and B, those fixed numbers A and B. Okay, so for example, if I write 1, 3, okay, so what am I saying? I'm saying that I'm taking A to be 1 and I'm taking B to be 3, correct? And what is that? You can rewrite this bubble here that you see, this cloud, as the collection of objects that are real numbers with the property that those real numbers should be at least the A, and who's the A here? Is the 1, and at most the B, and who's the B here? Is the 3. Correct? So pictorially, how does it look? If this is the number line, and this is 1 and this is 3, so what's the set? It contains all real numbers, so all real numbers that are between 1 and 3, Okay, Let's color them in orange. So any number that's between 1 and 3 is welcome. So this is obviously such a guy. Any guy here is also another guy that's welcome to the set, right? Any number between 1 and 3 is part of this interval, right? Bracket 1 comma 3, another bracket. But in addition to this, how about 1? Is it part of the set? Well, to be part of the set, it should verify this inequality. Meaning, if you replace x by 1, do you get a true statement? Well, this means two things. 1 is less than or equal to 1, and 1 is less than or equal to 3. For 1 to be a participant in the set, it has to verify this inequality, and it has to verify this inequality. Let's check this inequality here. Is 1 less than or equal to 1? Yes, 1 is less than or equal to itself. So this is okay then. How about this inequality? Is 1 less than or equal to 3? Yes, certainly 1 is less than 3. In particular, it's less than or equal to 3. So this is also okay. So if you replace x by 1, it verifies the membership. As such, 1 should be a participant in the set. So I'm going to baptize it in orange color. So 1 is part of the set. Okay. Let's try 3. Let's try 3. Let me erase these. How about 3? Is it part of the set? Well, to be part of the set, it has to verify the membership of the set. Certainly 3 is a real number. And now we're gonna replace x by 3 and check if this inequality and this inequality are both verified. If they are both verified, then 3 is gonna be part of the set. If one of them fails, 3 is not gonna be part of the set. Let's try. How about this first one? Is 1 less than or equal to 3? Certainly, this is correct. How about the second one? Is 3 less than or equal to 3? Is 3 less than or equal to itself? Yeah, it is equal to itself, so it is less than or equal to itself. So that's correct. So 3 then is part of the set because it verifies the membership. So as such, I'm gonna again go and write the 3 in orange to make just to indicate that the 3 is part of the set. Okay. How about if you pass 3? If you give me a number beyond 3, whatever the number is, if you give it to me, is it part of the set? Well, to be part of the set, it has to verify the two conditions that we just talked about here, the two inequalities. Any number that you take beyond 3, any number here that you take, sorry, let me change the color. Any number that you take here, outside or bigger than 3, whatever the number is, say y, that's bigger than 3 according to the picture, check, replace x by this y. Is y greater than or equal to 1? Meaning, is 1 less than or equal to y? Yeah, certainly, y is right there, and 1 is smaller than or equal to y. So this is certainly correct. How about the upper inequality, this one? Is y less than or equal to 3? This y that we chose that's beyond 3. Is it less than or equal to 3? No, it's bigger, right? This is our choice of y. So this fails, and since one of the two inequalities doesn't hold, so this participant y is not going to be welcomed in the set. Okay? In fact, any number beyond 3 is not going to be a participant in the set, and similarly any number smaller than 1 is also not going to be a participant in the set, right? Because again, let's take an element smaller than 1, let's say z, that's smaller than 1 by design, and replace x by z. Check, is this correct and is this correct? If they're both correct, then z should be part of the set. Let's check the upper one. Is z less than or equal to 3? Is this z, this guy, is it less than or equal to 3? Certainly that's correct, so this is okay. However, the lower inequality fails. Why? Because z, our choice of z was smaller than 1. So it's not the other way. It's not 1 smaller than or equal to z. Okay? So this z is not part of the set because this lower inequality fails. Okay? So as such, what's the set then? What's the set? 1 comma 3 with bracket here and bracket here. It's simply those orange elements. The first element is 1 and the last element is 3, and any number in between is a participant in this interval. Okay, so I hope you I hope this makes sense. So interval, because it's a continuum. Okay, it's the whole thing. Okay, and by the way, there are infinitely many elements between in any non-trivial element, in any non-trivial interval. For example, this interval here, which is of length 2 from 1 to 3, it has infinitely many elements. In fact, there are uncountably many elements. You cannot even count them. Okay. Don't worry about this part. I'm just telling you that there are infinitely many in between 1 and 3. Okay. All right. So back to this whole discussion here. If you want to remain in the abstract context, AB, how would you represent that for abstract context? Let me erase this part. Okay, let me erase all of this. Okay, so let's stay in the abstract context. This is the interval. This is the number line. This is where A is. This is where B is, because A is smaller than B. And any number between A and B, according to the description here, any number between A and B is welcome to the set. So let's color those guys as orange. So all these guys are part of the set. And now how far can we go? Well, the lowest you can go, exactly as we discussed before, is A, right? A is the first guy that you can invite, or the smallest guy that you can invite. Why? Because A verifies the membership. A is a real number, and A is less than or equal to itself and less than or equal to B. Correct? A is less than or equal to itself, and A is less than or equal to B because A is smaller than B, as you see here. All right. And the last element in this interval is actually B. Why? Because B is a real number. B is a real number. And if you replace x by B, it certainly verifies the double inequality here, because A is smaller than or equal to B because of this, and B is smaller than or equal to itself. Okay? And as we discussed before, if you pass B, or if you go smaller than A, you start being outside of this interval. Okay, sounds good. So such an interval has a smallest element, or a first element, A, and has a largest element, which is B. All right, moving on. This looks like, this image, which is an interval here, this image looks very close to this interval, but instead of having an angle bracket, now we have a parenthesis. Okay, and let's see the significance of this parenthesis. It's embedded in this writing. So this set is by definition the collection of all real numbers that are still between A and B, but they cannot actually reach A, but they are allowed to reach B. Okay, so the difference between this thing and this set, the difference is actually right there. Correct? So if the object is allowed to be A, then I'm having this bracket, And if this object is not allowed to reach A, it has to be above A, then we have parentheses. How does this translate pictorially? So let's draw our number line. This is A and this is B. What are the elements in the set? In this set, there are real numbers that are between A and B. Okay, so we know they have to be here. Any number between A and B is a participant in the set, like we used to have before. How about B? Is it a participant in the set? If you replace X by B, do you get a true statement here? Do you get the memberships correct? So if you replace X by B, do you get a true memberships? Is B a real number? Yeah, it's a real number. Is A smaller than B? Yeah, A is smaller than B. And is B smaller than or equal to itself? Yeah, B is equal to itself, and hence it's smaller than or equal to itself. So B is certainly in the set. Okay. Now, how about A? How about A? Is A an orange guy? If you replace X by A, do you get true statements? Do you get, does A verify the memberships? Is A a real number? Yeah, A is a real number. Is this correct? Is A smaller than itself? Is A smaller than itself? Of course not. So this fails. This one fails this time. Even though this one is not failing, this is okay. A is smaller than or equal to B, right? A is smaller than B, so it's smaller than or equal to B. But since this one fails, A doesn't verify at least one of the memberships, and as such is not part of the set. Okay, so we get this. So actually A is gonna remain a blue guy, is not an orange guy. But you can get as close to A as you want from the right without reaching A. Once you reach A, you become outside the set. Okay, so this is like a door here that's open. Think about this as being open. Once you reach that door, you start being in the other room, outside the orange room. Okay, so I'm gonna think about the parentheses as an open bracket, and this bracket here, this angle bracket, I'm gonna think about it as a closed door. As a closed door, I'm gonna call it closed bracket, because A is, the very first element in the set, so you're closing that door right there. And B also is an element in the set. It's the last one, so you're closing the door of the set right there. Okay, as opposed to here, it's open because there's no first element in some sense, right? All what you know is you can get as close to A as you want from the right, but once you reach A, you become outside, right? Because A is the first guy outside the set. Okay. All right. So let's summarize our findings so far, or our definitions. This image means the set consisting of all objects that are between A and B, including A, including B. So remember, closed bracket means you are including the endpoints. And this symbol means it's a semi-closed set. So on one end it's open, on the other end it's closed. So it's a set that doesn't have a start, but it does have an end. Okay. All right. Let me just erase those parts here. Oops. Okay. All right. How about this? How about this one? Well, this means exactly what you might think it means. It means Now the open door is going to be at B. So now B is not going to be invited to the set, yet A is going to be invited. So pictorially, or in set builder notation, it means the collection of all real numbers that are between A and B still, but those elements cannot reach B, but they can reach A. So you have the number line, you have A and B. Any element between them is part of this set, okay. A is part of it too, because if you replace x by A, you get a true statement, right? A is a real number and A is less than or equal to A, and A is smaller than B by design. But now if you go to the upper endpoint, B is not going to be part of the set because it doesn't verify at least one of the memberships. B is a real number, that's okay. A is smaller than or equal to B is okay. But the last one, B is not smaller than itself. So this fails, right? This inequality fails. And as such, at least one of the three demands for, or one of the three memberships is failing. As such, B cannot participate. Okay? And again, any number bigger than B is not going to be verifying those double, or this double inequality. Okay. Now you have parentheses on both ends, which means now you have open doors at both ends. So this means all numbers that are strictly between A and B. Okay. So again, if you want to use a picture, if this is A and this is B, what this set means is just a set consisting of objects that are only between A and B, excluding A, excluding B, right? You're not supposed to have an X that's equal to A, and you're not supposed to have an X that's equal to B. So just in between. Okay? Because if you replace X by A, this inequality is going to fail, and if you replace X by B, this inequality is going to fail, and as such A and B are not going to be part of the set. Okay. So what are the differences? I mean, how can we summarize everything that we have so far in this definition? Bracket, angle bracket means closed, so you are including that endpoint, and parenthesis means open, so you can get as close as you want to that endpoint, but you cannot reach it. Okay. How about we take just a quick example? How about we take again like 1, 3. Let's take it in this context like this. And let me ask you, is 1.1 an element of the set? Is 1.1 an element of the set? What's the set again? The set, if this is the number line, this is 1 and this is 3. Okay, so let me zoom in a little bit here so you can see it better. Okay, so if this is 1 and this is 3, everything in between is a participant, right? And 1 is not a participant because of the presence. This is indicated by this open bracket, which means you are talking about strict inequality. And 3 is a closed bracket, so 3 is invited, so 3 is an orange guy. Okay, 1.1 is somewhere here, so 1.1 is part of the set, so it's an orange guy. So that's correct. How about we take 2.99, say? Is it an element of 1, 3? Yeah, because 2.99 is smaller than or equal to 3, right? It's smaller than or equal to 3. It's right there. How about 3 itself? Is it part of 1, 3? Yeah, because if the x is 3 and the b is 3, 3 is less than or equal to 3, and the a in this case is 1. 1 is less than 3. How about 1? Is 1 an element of 1 comma 3? Is it a participant in this set? Certainly not, because 1 is not smaller than itself. Okay, so this lower inequality fails when a is 1 and b is 3. If you take x to be 1, 1 is not less than 1. Okay, so 1 is not part of the set. All right, very good. Let's keep going. Let's look at this this interval minus infinity to a with this same close bracket. Well, this again by definition, again we don't know what it means until we read what comes next, right? This is the meaning of the colon here. It's the collection of ordinary numbers that verify the following condition. Those numbers should be at most a. So pictorially you have the number line. Say this is minus infinity to plus infinity, the whole thing. And now you have a somewhere. So this set consists of objects which are real numbers, so they are part of the line, but not all of them, just those which are at most a. So let's again color them in orange. Such a number, this is a guy verifying this condition, right? It's a real number and it's less than or equal to a. It's to the left of a. Any numbers over here is verifying the membership to the set. And how far can we push? How far to the right can we push? Well, can we get to a? Is a part of the set? If a is part of the set, it means you can replace x by a, and that's gonna be correct, and that's gonna be correct. Are they correct? Certainly a is a real number, so that's correct. And a is less than or equal to itself. So as such, a is verifying the membership to the set, and hence a is part of the set. So I can actually make a an orange dot. Okay. Now if you pass a to the left, to the right, if you pass a, which means you're giving me a number bigger than a, obviously it's not gonna verify this inequality, and as such, you're giving me an element outside of the set. Okay. So that's the set, and same meaning. Angle bracket, it means is a closed door. It's the last element, right? It's the last element of the set. Okay, so since we talked about the closed bracket, now we're going to also talk about the open bracket, and it means exactly like we described before. Minus infinity to a means all real numbers that are smaller than a, and that's it. Not smaller than or equal to a, smaller than a. So on the picture, this looks like this. If this is minus infinity plus infinity, if that's a, so we're only concerned about points that are to the left of a, excluding a. You're not supposed to get a in the set. So all these numbers are still part of the set, but now there's an open door at a, right? Because a is the first element outside of the orange set. Okay, because again, if a is a participant in the set, it means that if you replace x by a, you should get a true statement. It should verify this membership and this membership. Well, a is a real number, that's okay, but a is not smaller than a, so that fails, and as such a should not be part of the set. Okay, all right, so it's just this array here, right? Okay, so in a similar fashion, we're gonna play the same game now to the right. If that's the number line, what is this set? What is this set? A to plus infinity with a closed bracket at A. It's the collection of ordinary numbers. You should have the intuition by now in terms of what this means. It's the collection of ordinary numbers that are at least A, right? At least A. So if A is here, any number bigger than or equal to A is part of the set. So A is part of the set because A is bigger than or equal to itself, so it's an orange dot. Any number bigger than A is also part of the set. Okay, because any number here certainly is bigger than A. And A is the very first element because A is equal to itself. Okay, now the open door, the open bracket, the parentheses, you're gonna exclude the A as usual, right? So let's give a picture for this again. Minus infinity to plus infinity. You have A here, the collection of, this is the interval that doesn't have a first element, right? Any number bigger than A is part of the set, that's it. It doesn't have a very first element. So any number here. Okay. Very good. And lastly, this interval minus infinity to plus infinity, it means just the collection of ordinary numbers. There's no constraints anymore. You don't see a constraint like this, a constraint like this, right? Any real number is invited to the set. So we're talking about actually the whole thing here, right? So this is actually the whole thing. That's minus infinity plus infinity. So all the line is actually orange now. Okay. So this is nothing more than just talking about the whole real line, right? The set of all real numbers. This is what this set is. This is the collection, see curly brackets, collection of all real numbers. Well, what's the collection of all real numbers? It's the set of all real numbers, right? Okay. All right. So here's a question. So the first question goes like this. Is there some number in this interval close bracket A all the way to B open at B that's greater than any other number in AB? So is there like a rightmost element in this interval? What's this interval again? AB. It's this set. So this is A, this is B, right? Okay, let's take it further, maybe here. And we know that according to our earlier discussion, we're talking about this one, right? A is part of the set and B is not. So A is an orange element and B is not. B is still blue. Okay? And anything in between is part of the set. So the question is, is there a number within this set? Is there an orange element? This is what it means. Is there an orange element that's greater than any other orange element? Right? This is what the question is. Is there a rightmost element in AB in this interval? To put it in perspective, let's talk about how about A being, I don't know, maybe 0 and B to be 1. Okay, just to put it in perspective. So we know that A is orange, so we know that 0 is orange and B is 1, so 1 is blue. The question is there an element that's the last one here? Is there a last one? You might think about 0.9, right? 0.9 is there somewhere. But 0.91 is after it, right? Correct? So if 0.1, if that's your guess to be the largest element in the interval 0, 1, well, 0.91 is after this. You're gonna say, oh, okay, let me modify my choice. How about 0.99? Well, if you go for 99, I'm gonna go for 991. 991 comes, 0.991 comes after 0.99. So still 0.99 is not the best. And then you're gonna play the game. How about we add one more 9, right? How about we add one more 9? So 999. I'm gonna go to, as you might guess, 9991. 0.9991 comes after 0.999, and as such 0.999 is not the largest element. Okay, so probably you're gonna say then, alright, I'm not gonna stop after a certain number of 9s. I'm gonna keep going, 999 forever. As such, I cannot play this game, right? I cannot put the 1. This might be the best guess. Am I correct? So your guess would be 0.9999, etc. Let me pause here for a second. Let me keep the context, the discussion in the abstract context. Let's stay within AB. Okay? So, if you say that there exists a largest element, let's call it, I don't know, G, the greatest. Okay? If there exists a greatest guy here, maybe the 0.999, etc., whatever that thing is, certainly G is part of this set, right? G is part of this interval. So let's suppose that there exists a largest element call it G and AB, right? So G, so thus G has to be between A and B like this. Am I correct? Because any element in AB in this interval, if you remember, any element in this interval AB has to be at least A and smaller than B. That's exactly what I'm saying. Since G is an element in AB, it's the largest element. So since it's within AB, it has to verify this. And it's the largest among all of them. I'm saying, okay, how about let's suppose this happens. Okay. Then what can we say? Let's create a number. Let's create a number that's between G and B. How about the midpoint, halfway? How about the midpoint between G and B? Let's call this number M for midpoint. Okay? So this number actually can be found. It's B plus G over 2. Let's call it M. So then, let M be a point halfway between G and B. Correct? So one more time. I'm assuming there exists a largest element. Like you gave me 0.9999 in the context of 0, 1. Right? You gave me this. That would be, to be more precise, that would be actually your G, correct? Okay? Just to be very clear. That would be your G in the context of 0, 1. So let's suppose that something like this happens, or yeah, it's the rightmost element in the interval AB. As such, I still have a room here to choose a number between G and B. How about you choose any number between G and B? How about the midpoint? Okay. This midpoint, M, is certainly an orange dot. Why? Why is that? This midpoint, M, is certainly an orange dot. What does it take for this M to be an orange dot? It has to be between A and B, correct? So therefore, m is smaller than b. Why m is smaller than b? Because it's halfway between g and b. Certainly it's smaller than b, right? And m is greater than g. Why? For the same reason, because m is halfway between g and b, but g in turn is bigger than or equal to a, right? G in turn, you see this guy? Let me highlight it for you. You see this guy? It's right there. G in turn is bigger than or equal to a. So this happens. So now if you put things together, what can you say? You have m smaller than b and m is bigger than a, right? So these two allow you to write that m is greater than or equal to a and smaller than b, correct? Maybe I should box this guy like this. One more time. I'm supposing that exists a largest element, call it g, your 0.999, etc. That's a guy, that's an orange guy, and I'm choosing an element, little m, which is midpoint between the supposed largest element and b. I'm making the case that little m is orange, which means little m is smaller than b and little m is greater than or equal to a. This is what it means for little m to be orange. And I just made the case. Little m is smaller than b because it's halfway between g and b, and little m is greater than g, which in turn is greater than or equal to a. So all in all, you get that m is smaller than b and bigger than or equal to a. So you get this. So m is an orange dot. M is an orange dot. So the picture is correctly illustrating the situation, right? M is an orange dot. All right. So what can we say? What can we say then? M is an orange dot that's bigger than the supposed largest element, right? So hence M is an element in this set AB like this, yet M is larger than G. So M is an orange dot and bigger than the supposed largest element in that set AB. So what can you say then? Such a G cannot happen. This contradicts the fact that this contradicts the assumption that G is existing. Make sense? So this contradicts. Or this contradiction proves that such greatest number doesn't exist. In AB. Okay. So one more time. Let's look at the big picture. What's the question? The question is, does there exist a largest element in this semi-open interval, right? It's closed on one side, open on the left side. So is there a largest element? Once we took the example 0, 0, 1, when we took the example A to be 0 and B to be 1, we came to the conclusion that this is a potential element. So it seems that there exists a largest element. So I went back to the abstract context to because I don't want to talk just about 0, 1. I want to talk about an abstract context, AB, because the question is about abstract context. So if such a number G exists, if there exists an orange dot which is the largest, I found an element which is also orange yet bigger than the supposed to be largest. So what does it mean? I just contradicted the fact that this G exists. So this G must not exist then. Okay. Now you're gonna tell me, oh, how about 0.999 in that case? What is that? I mean, 0.99. Why this is not in the context of 0, 1? Why this is not the largest element? Well, as it happens, this is actually 1. This is actually exactly 1. It's not an approximation of 1. It's exactly 1. Okay, it equals 1. And we're gonna see this when we talk about series towards the end of the semester. Okay, so so that guy 0.99, it was a good guess, but as it turns out, you're gonna see this in the future, this is actually equal to 1, and 1 obviously is a blue dot, it's not orange. So you gave me a number that's not orange to begin with, and you claim that that's the largest orange. Since it's not orange, it cannot be the largest orange, and as such that choice is wrong. Okay, all right, I hope this makes sense. Number 2, is there some number in this interval AB that's smaller than any other number in AB? So back to this, in AB, is there an orange dot that's smaller than any other orange dot? That's easy. Yes, A is that guy, right? Yes, A is that guy. A is in AB and is smaller than any other element in AB. Oops, let's open AB right this. Okay. So that's, if you wish, that's the leftmost element in the set. Okay. All right. 3 and 4, it's the same game as 1 and 2, but now we reverse the parentheses. I'll let you finish these two as exercises. So 3 and 4 are left as exercises, and we'll discuss them during our class time. Okay. Next definition. Given two sets A and B, so given two sets A and B, so capital A and capital B are both sets, we're gonna define a new set out of these two sets, and we're gonna call that new one intersection of A and B. So the intersection of the sets A and B, denoted by this symbol, so this is not the letter N, this is an operation between the two sets. This means the intersection between A and B. And what is that? It means, again, what you might think it means. It's the set consisting of elements that are at the same time in A and in B. Mathematically, this is how you write it. A intersect B, it's a set, so you're gonna have curly brackets, consisting of objects. Let's call a generic object X. And what's the membership to the set? That X should be at the same time in A and in B. Correct? So how can you picture this, if you will? If this is the set A, if that's the set A, and that's the set B, what are the objects that are at the same time in A and in B? Is this guy such an object? Is this guy a pink guy and a purple guy? Let's call the guys that are in A pink and the guys that are in B purple. Is this guy bicolor, pink and purple? No, this is just pink, right? It's not part of the purple region. How about this guy? Is it pink and purple? No, this is just purple because it doesn't reach the boundary of, or it's not within the boundary of the set A, right? However, this guy here, or such a guy, is at the same time pink and purple, right? So any guy in this region is part of the intersection. It's the overlapping, it's the intersection, it's the overlapping region. So that's the intersection. It's right there. Okay, so this area here, that's the intersection part. Okay. So A intersect B is one set that's made up of two sets. It's one set, it's this set. It's where the two sets meet. It's the collection of objects that belong simultaneously to A and to B. Okay. All right, let's take examples. Let's look at the first one. Clearly determine the following sets. So you have this set, which consists of numbers that are -1, 0, and 1, and you wanna take the intersection of this set with the other set, which is also made up of 3 elements, but now these elements are 0, 1, and 2. So according to the definition just given above, the intersection between two sets is the collection of objects that belong to both sets at the same time. There's an and here, right? The ampersand. These objects that belong to the intersection are at the same time in A and in B. So what is this thing then? Well, this is the collection of objects that are in this set and in this set. Well, -1 is only in this set, it's not part of the set, so it should not be part of the intersection. 0 is in this set and in this set, so 0 is part of the intersection. 1 is part of this set and part of this set, so it's also in the intersection. And that's it. 2, obviously I don't see it here, so it's only on one side. So if you want to put it in this perspective over here, we have -1, 0, and 1. That's for A, right? And for B, you have 0, 1, and 2. So that's why the intersection was just 0, 1. Okay? Alright. Just move this a little bit this way. Next. This example, part 2. You're going to find the intersection between those two sets. The first one is made up of a triplet, 3 elements, -1, -2, -3, and the second is also a triplet, but now just 1, 2, and -3. So what's the intersection here? So what are the objects that belong at the same time to both sets? -1 doesn't belong to both. -2 doesn't belong to both. -3 does belong to both, so that's the guy. So the intersection in this case is just a singleton. It's just a set consisting of one element. Okay. By the way, there's a big difference between writing this and this. This is a number and this is a set. Okay, don't confuse the two. This is a set. This is a basket which has the object -3 inside. This is just an object. Okay. So if you erase the curly brackets and you just keep the -3, it's not an answer, because the intersection of two sets must be a set. It's not an object. Okay. All right. Third part. Z intersect N. What's Z? If we go back to an earlier page, Z was the set of all integers, and N was the set of all natural numbers which are positive integers. So what's the intersection between the two? What is that? Pause the video please and think about it on your own. Well, the intersection is simply n in this case. Correct? The only guys that are in Z but not in N are the non-positive guys. They are 0, -1, -2, and so on, right? Let me try to show you this page again. So we are talking about this very first page. It's right there. You see N? It's the set of all positive integers. Z is the set of all integers. So the only guys that are in both are just the 1, 2, 3, etc. The positive guys. The non-positive are not there. They're not in the intersection because they're not in N. Okay. All right. So back to this. You might think, okay, how does it look pictorially? I mean, what is the corresponding picture to this situation? Well, the situation here is like this. The pink part is let's say Z, so that's Z. But the purple part, you see, it doesn't have an area outside. N is entirely sitting inside Z, right? N is entirely sitting inside Z. Why? Because natural numbers are already integers. So certainly those guys are part of Z. So what's the intersection then now? What's the intersection between Z and N? It's the smaller one. It's the trace. It's the smaller one. And this is true in general. If you have two sets, one sits inside the other, the intersection is the smaller one. Okay? Alright. How about this? -10 to 1, closed at -10, open at 1, intersected with the set or the interval between -1 and 5, including -1 and including 5. Alright. Let's actually have a picture, a number line picture here. Let's move this a little bit down. So this is the number line. Okay. Let's call those guys pink guys, and let's call the other guys purple guys. Where are the pink guys? Well, the pink guys are between -10, including -10. So -10 is the very first guy that's pink, all the way to 1. All the way to 1. But 1 is excluded. Remember the open bracket? The parenthesis means that 1 is not part of the set. So 1 is gonna be just blue. Right? 1 is blue. So this pink, in this collection is the collection of all the pink guys. Now, the purple ones, those are members or elements between -1 and 5, possibly -1, possibly 5. So -1 and 5 are part of the set. -1 is here, right? And 5 is here. Say, and 5 is purple because you see the closed bracket, right? There's a closed door here, closed door here. So all these guys are purple, right? We know now that one is purple, right? 1 is purple. So 1 is purple. Now the question is, what are the guys that are at the same time pink and purple? So what are the guys on the picture that are at the same time that have the two colors, that are bicolored? pink and purple. Well, -1 is purple and it's pink. So -1 is there. Anything before -1 is all the way to -10 is purely pink. It's monocolored. And anything from 1 onward is monocolored all the way to 5. Correct? So the intersection is simply just between -1 and 1, including the -1 because we said -1 is pink, and excluding the 1 because the 1 is only purple. The 1 is only purple, it's not pink. Okay? So the answer is just those guys, including this endpoint -1. So -1 closed, all the way to 1 open. Is this the same as only -1 and 0? Is this set the same? Is there any other guy inside the set other than -1 and 0? Certainly -1 is here, right? So certainly -1 is in the intersection. Certainly 0 is in the intersection because it lives there. But are these the only guy inside the set? Certainly not. There are many guys. I mean, let's highlight the -1 and 0. -1 is this guy and 0 is this guy. So you're missing all these pieces. Okay? You're missing all these pieces. And as I mentioned before, there are infinitely many, and as a matter of fact, there are uncountably many. You cannot even count them, let alone being infinite. Okay? So don't confuse this with those two. Those two are part of the set, but they're not the set. There are many, many more inside. So anything here between -1 and 0, and anything between 0 and 1 is there, right? Okay. Alright, so okay, let's talk about this. 5, 7, so the interval 5, 7. Actually, how about you do this as an exercise? So I'll leave this as an exercise. How about this one? So that's the collection of all numbers that are between 5 and 7. I want to intersect this. Oh, by the way, 5 is part of the set, 7 is also part of the set. I want to intersect this with the set consisting of numbers that are between 7 and 10, excluding 7, including 10. So what's that intersection? I encourage you to do the same picture as I did before, very close to it. And the only thing you might guess is probably 7 is in the intersection. Well, 7 is certainly in this side, but it's not in this side. Remember, parenthesis means open. So 7 is not here, but 7 is here. So it cannot be in the intersection because it's not in one of them. To be in the intersection, it has to be in both. If it's not in one, it cannot be in the intersection, correct? So since 7 is not here, it cannot be in the intersection anymore. So what's the intersection then? There's nothing in the intersection. So the intersection is actually empty. So this is the empty set. It's a set consisting of nothing. And there is a symbol for this. So there are two ways to represent this. Or I know of two ways, probably more, but any notation, once you define it, can do the job. This is a set consisting of nothing. It's an empty set, right? And the universal notation for empty set is actually also, it can be this, but it's also this thing. And this is Greek letter phi. So this is the Greek letter phi. Okay, so phi, what is it? It only denotes the empty set. It's the set consisting of absolutely nothing. It has nothing in it. Okay. All right. Let's Let me just color this something else. Okay, there we go. Very good. Alright, lastly, I have an intersection between two sets. The first set is this guy, and the second set is the set of natural numbers. Okay, we know what this set is. What's the set? This is the set of positive integers. So 1, 2, 3, 4, etc. How about this? How about this purple thing? Let's understand the membership of the set. The membership is, they should be real numbers, but once you square them, you get 1. What are the real numbers so that if you square them, you get 1? There are two guys, 1 and -1. Correct? So this set is simply -1 and 1. Why? Because, I mean, these are equivalent things, right? They are the same. This bubble here means the collection of numbers that are real numbers, such that if you square them, you get 1. There are two real numbers that do this job. It's namely -1 and 1. So these are the constituents of the set. So this whole cloud means the doubleton -1, 1. It's the set consisting of just those two numbers. Now I have a better understanding of what this is then. The purple means -1, 1. The set consisting of -1, 1 intersected with n. Right? I'm rewriting it using what this means. It means that. So we get this. Now it's better. What's the intersection between this doubleton and the set of natural numbers? Well, -1 is not in the natural numbers, but 1 is in the a natural number. So what's the intersection then? It's just the set consisting of just 1, right? Correct? So again, intersection means I'm looking at elements that belong here and here at the same time. The only guy that's here and here at the same time is 1. Okay? Alright. Another operation between two sets, and that's the union. Let's see the context. Let A and B be two sets. So there we have capital A and capital B, each of which denotes a set. We're gonna talk about the union of A and B. The union of A and B, denoted by this symbol, it's a reversed intersection, right? This looks like a cup. Okay, so that operation means union. So the union between two sets, and what is it? It's the set consisting of elements that are in A or in B. And when we say or, we also mean or in both. Okay, so that's the inclusive or. So elements that are in any of the two should be part of the union. Mathematically, this is how you write it. So the union between A and B is, by definition, this is just the definition, consisting of, it's the set consisting of objects, let's call it generic one X, objects that are either in A or in B. And remember the word or that I just said, it's the inclusive or, so which means or in both. If it's in any of the two, it's in the union. Okay. Think about the situation. If you get married to someone, you have two families: family A, family B, for the guy, for the girl. The union of the two families becomes the bigger family, right? Because once they get married, they kind of become one bigger family. You may have common guys, maybe uncles or I don't know. You may have common guys. Um, those common guys are still part of the bigger family. Okay. All right. So pictorially, how does it look? If that's the family A, or this is the set A, and this is the set B, okay? To be in the union, it should be either an object to be in the union, it has to be either in A or in B or in both. It has to be in any of the two. How about a guy here? Is it part of the union? Yeah, it's part of A, so certainly it's in the union. So all these guys are part of the union. Let me just change the color. So all these guys are part of the union. Any pink guy is part of the union, right? A guy here as well, because it's part of A and part of B, but in particular it's part of A, so it has to be part of the union. How about the guy in B? Since it's in B, it's in the union. So I'm gonna extend this and I'm gonna get the whole thing. So the union actually is just the whole thing. Okay, so that's the A union B. So these would be, in the case of marriage and so on, these would be non-common relatives. These would be also non-common relatives, and these are common ones. But those common ones remain in the bigger family, in the union of the two families. Okay. All right, example. Clearly determine the following sets. Let's take the first one. You have the union between the set consisting of 1, 2, 3 and the set consisting of 2, 3, 4. What's the union between the two? Think about it. So it's the set. Any guy in any of the two is going to be part of the union, as we just described. 1 is in the union for sure. 2 is also in the union. 3 is also in the union, right? These are all the elements of A. 2 again, but 2 was accounted for, right? So this is a common relative. It's already there. We don't list it another time because, I mean, I already listed it. I already accounted for it, right? It's like on my roster, if I have you, there's no need to re-mention your name again on the roster because it's already accounting for you. All right, so 3, similar reason. 4, that's the last guy in the union. Okay. By the way, the order in a set doesn't matter. This is the same thing as 4, 1, 3, 2. Okay. As long as you list it, it's there. That's it. So as a list, as a roster, as a family, they are the same. As a set, as two sets, they are the same. Sure, I shuffled the elements, but still, I mean, I'm still talking about the same elements, the same collection. Okay. All right. All right. How about this? This is the collection of all even integer larger than 1. So any even integer larger than 1. So what are we talking about here then? What is this? What is this guy? Any even integer larger than 1. So it's the set consisting of 2, 4, 6, 8, and so on, right? Realize I put the dots because the pattern is now understood. It's just the even. You just add 2. Okay. So all this thing means the set consisting of 2, 4, 6, 8, all the even integers larger than 1. And how about the other guy? How about this guy? It's the set consisting of all odd integers larger than 1. So what is this guy then? What are the odd integers larger than 1? So they are 3, 5, 7, 9, etc., right? And now you're gonna take the union between those guys and those guys. What do you get? So what do you get? You get 2, 3, 4, 5, 6, and so on, right? You get a huge piece of the natural numbers. So you get all the natural numbers except the very first one. Okay? All right. Okay, so lastly, for this exercise, you have a union between three sets. Minus infinity to minus 1, union minus 1 to pi, union pi to plus infinity. Pay attention here. You have minus 1 is not part of the set. Minus 1 is part of the set, so should it be part of the union if it's not in one of the two, but it's in the other? Yeah, because the union, you just adjoin them, right? If it's not here, it's here. It's certainly a part of the union. And pi is here and also here, so certainly it's in the union. Okay, so draw a picture here, but I hope that you see. I'm gonna put an exclamation mark here just to make sure that there is some thinking maybe. But if you don't get it, talk to me during class. I'll be happy to explain it to you. I hope you see that this is actually all of R. Okay. Draw a number line, minus infinity to negative 1. You adjoin this to all the guys. You know what? I'll explain it. So this is the number line. Minus infinity to negative 1. Let's call those guys pink. Where are the pink guys? Minus infinity all the way to negative 1. Negative 1 is not pink, right? It's gonna be just blue now for now, because negative 1 is open. Now you're gonna adjoin those elements, those pink elements, to those guys. And let's give them a color. How about orange? So those guys are gonna be from minus 1 all the way to pi. So minus 1 is orange, all the way to pi. Pi is somewhere here. So all these guys are orange. And then you're gonna adjoin what you just adjoined. You're gonna join them to new guys, which are, let's give them a color. About green. About purple. Did we use purple? No. Okay. So how about purple? So pi all the way to infinity. So pi is also purple, right? And all the way to infinity. So you're gonna take the union. You're talking about the union of the pink, brown, what is it? Maybe orange and purple. When you talk about union, you mean it's at least in one of these three sets, right? So this is family 1, family 2, family 3. The union of all of these is gonna be the collection of all the guys that are in any of them, right? So any guy that has a color is gonna be part of the union. Well, look at it. Any guy here on the number line is either pink, orange, or purple. So that's why you get everything. Okay. All right. Here's an exercise for you to be discussed in class. Okay. So you have two sets, A and B. A is the set of even integers, and B is the set of prime numbers. Question is, I hope you understand what prime number is. Prime numbers are numbers that are bigger than 1, and the only divisors are just itself and 1. Okay, so for example, 2 is a prime, 3 is a prime, because it's bigger than 1, and it's the only divisor of 3 is itself and 1. Correct? So a prime number is a number, let me define it for you. So recall, a prime number is a number that's bigger than or equal to 2 or bigger than 1. Okay, so it's not any number, it's an integer, I should say. Is an integer that's greater than 1 and its divisors are merely 1 in itself. Right? So 2 is a prime number because 2 is an integer that's bigger than 1 and its divisors are only 1 in itself. 3, 5, 7, etc. 1 is not prime because 1 is not bigger than itself, right? Okay. Alright. So the question here is find the intersection of those two sets, and the second part, provide an element that's not in the union. Provide an element that's not in the union. Okay. Alright, let's keep going. Here's the next definition. Let A and B be two sets. So you have A and B that are two sets. Let's give ourselves a picture. Maybe this is A and this is B. We're gonna define the set theoretic difference of A and B, denoted like this. It's A with a backslash or minus B. Okay, so this is set theoretic difference of A and B, and it's defined like this. It's the collection of objects that belong to A but not to B. Okay, it's the set consisting of elements that belong to A but not to B. If you want to read it mathematically, it's the collection, right? The set theoretic difference of A and B, it's the collection of objects that are in A but not in B. Let's shade the region corresponding to this. That are in A but not in B. How about this guy? Is this guy in A not in B? Is this guy a guy in A and not in B? Yes. So all this piece is part of the set theoretic difference, right? How about the guy here? Is this guy in A but not in B? This blue guy? Well, this is in A but also in B. So this blue guy is not in the set theoretic difference. How about this guy? Is this guy in A and not in B? Oh, certainly this guy is not even in A. Okay, so this guy is not part of the set theoretic difference. So this blue region is actually A minus B, the set theoretic difference of A and B. Okay, so that's A minus B. Okay. So it's like it's a relative complement. Okay. Anyway, forget it. One more time. A minus B, it's the collection of all the objects that are in A, not in B, and they look like this. Okay. Represent the set, this guy, R minus 3, using interval notation. So, according to the definition we just discussed, this means the collection of all numbers that are in R, but not 3, right? Correct? So let me write it for you. R minus the singleton 3, according to what we just said here, A is R and B is the set consisting of just 3. This is the collection of numbers. I'm just copying this. This is the collection of numbers such that this number is in A. Who's A? It's R. And this number is not in B. And who's B? It's the singleton 3. Correct? So it becomes like this. And take a look. What does this mean? This is the collection of all real numbers that are not 3. Right? The collection of all real numbers that are not 3. So everything except 3. How does it look on the picture, on the number line? If that's the number line, what are those guys, the green guys? Any number that's not 3, that's on the number line. The only guy that's not green is 3. Correct? So all of them except 3 is green, are green. So let's say the green one is, let's say that this guy is red. That's the guy 3. That guy is the only guy that's not green. Okay? Again, let's read this. This means the collection of all numbers that are not here. What does it mean that x is not in the singleton 3? This means x is not 3, right? This means x is not 3. X is not 3. That's what it means. What it means that x is not in the set 3. The only guy that's in the set is 3. So if x is not there, this means x is not 3. So as such, we can say that this is the collection of all real numbers that are different than 3, right? Correct? As the picture indicates. Now they said here they want to use interval notation to write this set. How would you represent this using interval notation? Well, I can write this guy as minus infinity to 3 open, and then 3 to plus infinity, right? Union. I can adjoin the two. So I can take minus infinity to 3. This would be this guy. I'm gonna adjoin it to this piece. And what's this piece? 3 to plus infinity, correct? 3 to plus infinity. So one more time. The question is, represent this set, which means all the green guys, using interval notation. Well, interval notation using those guys, right? The intervals that we just discussed above. Well, how can we do it? We're gonna take all these green guys, and what's the way to represent all these green guys? This ray here, it's minus infinity all the way to 3. That's the interval representing this piece. We're talking about that. And I'm gonna adjoin those guys to this piece. And what's this piece? 3 to plus infinity. Again, I'm gonna have open at 3 because I'm gonna exclude 3. Okay? So, long story short, at the end of the day, this guy here is simply this guy. So you can either use this writing or this writing. Okay? I'm just giving you the various ways of representing a set. Very good. Express in words the set Z minus N. I'm gonna let you complete this as an exercise to be discussed in class. So, oops. So, to be discussed in class. Okay. Exercise to be discussed in class. So what's that set? Z minus N. So you chip away all the positive integers from the integers. What are you left with? Think about it. Okay. Here's another exercise to be also discussed in class. It goes like this. If you have two sets, A and B, with the property that if you chip away b from A, you get b. What can you say about the sets A and B? So, I'm not going to say anything further, but think about this little puzzle here, okay? Again, we discussed this piece in class. All right. The last part of the review slash terminology is about the nth roots. Let's recall the following. Let n be a natural number, meaning positive integers, and x be a real number. If n is even, remember what this means? The nth root of x. If you call this k, by definition, this means that k to power n should be x, and k should be non-negative. For example, when we talked about the square root of, I don't know, 4, right? So square root of 4, let's say here. Oops. All right, just a second. One more time, let's do it. So let's say the square root of 4. By the way, when we don't write this index, this n is called index. When we don't write it, it means it's 2. So I'm gonna color it with a different color just to let you know that we're not supposed to write it. I mean, it's a convention. Whenever we don't write it, it means it's 2. So this means the second root of 4, or the square root of 4, this is equal to k. And what does it mean? What is this number k? Well, this means if you take this number and you raise it to this power n, which is 2, the purple guy, right? The purple guy, you should get back the x, which is the guy under the umbrella, which is 4. Well, I have two guys that do this job. I have 2 and negative 2. If I square 2, I get 4. If I square negative 2, I also get 4, correct? But this condition is going to tell me exactly which one to choose. This condition, k is bigger than or equal to 0. So out of this, I could have said, oh, I have two choices. I have the k equals plus or minus 2, correct? If I square the 2, I get 4, and if I square the negative 2, I get 4. But this one is going to tell me, okay, throw away the negative, just keep the non-negative. So what's the k then? K is going to be plus 2. So long story short, this guy is equal to the k, which is 2. Okay? Alright. So when n is even, since you have two choices, whenever, look, if n is even, if you raise any number to an even number and you get x, you can raise its opposite and to that number n and also get x, like we did here, right? If you raise 2 to power 2 and get 4, you can also raise the negative 2 to power 2 to get 4, because when you raise to an even power, that sign is absorbed. It doesn't matter whether you take the plus or minus, correct? So, and this is the case whenever this power is even. It doesn't have to be just 2. Okay? So since you have two choices here, that guy is going to be the tiebreaker. Just get the non-negative one among those two guys. Okay? Alright. And on the other hand, for odd numbers, what does this symbol mean? This symbol means it's a number so that if you take it to the nth power, you get x. Observe here, we don't get this part, because for odd powers, there is one and only one guy that does the job. So there's no, you don't need a tiebreaker to actually determine which one to be chosen, because there is one and only one guy that does it. Okay? Alright, I mean, this is an entire section by itself in earlier courses. I just wanted to extract one piece of information which is embedded here in these two bullets. And the information is like this. Allow me to just erase this part so I can explain a little more here. Okay, so look, in the context when n is even, k to power n, right? If you raise any number, any real number to an even power, what do you get? If you raise any number to an even power, you get a non-negative guy, right? This is certainly greater than or equal to 0. This is certainly greater than or equal to 0. And who's this guy? It's x. So what can you say then? When n is even, the x, which is the guy under the umbrella, should be greater than or equal to 0. And that's this guy that I have here. If n is even, for this writing to be meaningful, to exist as a real number, you must have the guy under the umbrella to be 0 or more. Okay? This is not the case when n is odd. When n is odd, you can plug in anything under the umbrella. Correct? As we just discussed before. Alright. One more time. These are the two bullets that I care about from earlier courses. These things you should have seen before, but I'm revisiting them just to extract these two pieces of information. The first one is, for an umbrella with an even index to be meaningful, to exist, meaning to be a number, I have to have the guy under the umbrella to be non-negative. For example, I cannot have square root of -5. This is nonsense. This is not a real number. Okay? This is not a real number. So this does not exist. For it to exist, I need this guy to be a non-negative guy. I'm allowing it to be 0 at worst, but it cannot drop below 0, like -5. Okay? Alright. And when the index is odd, you can put here anything you want, right? Based on this definition. Alright, let's put this in action. Find all real numbers x for which the algebraic expression square root of 2x minus 1 is defined as a real number. So the question is, what can I plug in here so that this expression becomes meaningful, becomes a real number? Okay, so that's the question. Please pause the video and take a moment to think and discover things for yourself. Alright, so what are the numbers that can be plugged in here so that this whole thing becomes meaningful? Let's try. If you plug in 0 here for x, this becomes 2 times 0. So if you plug in 0, this becomes 2 times 0. And what's 2 times 0? That's 0. 0 minus 1 is -1. So the whole thing becomes square root of -1. That's nonsense, right? This is not a real number. So I cannot plug in 0. Alright. How about if I plug in -2? Well, if I plug in -2, this becomes 2 times -2, so -4 times -1, it becomes -5, so it becomes square root of -5. Also doesn't make sense. How about you plug in 1? If you plug in 1, you get 2 times 1, which is 2, minus 1, that's 1. 2 minus 1 is 1. Square root of 1 is meaningful. Square root of 1 is a real number. It's 1 actually. So it looks like some numbers work, some numbers do not work. The question is, find all of them that work. Not just a couple or one, just all of them. Alright, so we have to appeal to this bullet. What does the bullet say? This bullet says, if the index n is even, what's the index here? We just said, whenever we don't write the index, it means it's 2, right? So the index is 2. I'm gonna write it just for you to see it. So the index is 2, certainly is even. For this to exist, You're gonna say, oh, here I have x, here I have x. Don't worry about the x. X is like a placeholder for the guy under the umbrella. If you don't like x, all right, let's have a placeholder for it. I'm gonna how about star? Okay, that's the same guy here, right? That's the same guy. Okay, so the nth root when n is even, the nth root of something is meaningful, it exists, if and only if that thing, that guy under the umbrella is bigger than or equal to 0. Okay, so that's what I'm going to employ here. Who happens to be the star in this case? It's the 2x minus 1. That's the guy that's taken the role of star. That's the guy that's taken the role of the guy under the umbrella, which is represented by star here. Okay, so by the first bullet above, right? By this I mean that guy. The square root of 2x minus 1 exists, which means is well defined as a real number, if and only if the guy under the umbrella is non-negative. And who's the guy under the umbrella? It's the 2x minus 1. The guy under the umbrella is non-negative. Okay, so this algebraic expression is meaningful as long as the guy under the umbrella is non-negative. Alright, now it becomes a linear inequality in one variable. How do you solve this? I hope you are familiar with this. How do you solve this inequality? You can add 1 to both sides. You get 2x greater than or equal to 1. And then you divide by 2. Since you're dividing by a positive entity, you don't have to reverse the inequality sign. You keep it the same. So you get 1 over 2. Okay? So you get this. So this tells you exactly what you can replace x with. It tells you exactly what you can replace x with. That's what I wanted, right? You can replace x by any number that's half or more. Remember, we plugged in 1 at the time and it worked, obviously because 1 is bigger than or equal to half. The 0 and the -2 at the time did not work because they don't verify this inequality. Okay, 0 is not greater than or equal to half, and -2 is not greater than or equal to half. So those are the only guys that you can plug in here for this to exist. And the if and only if guarantees that there are no more than those guys. Okay. So what are all the x? They are all the numbers that are half or more. So to conclude, square root of 2x minus 1 is meaningful precisely when x is greater than or equal to half, which means x is an element of this set, half to plus infinity. Correct? Remember this? That means any number that's half or more. So we're talking about those guys, right? You're gonna tell me, oh, which final answer do you prefer? You decide which one. I don't mind any of the two, as long as it's a correct answer. I'm okay with it. So the answer here, the question is, find all the real numbers that make this algebraic expression well defined. Well, if you tell me any number that's half or more makes this algebraic expression meaningful, I'm happy. If you write any mathematical thing, as long as it's correct, I'm happy. If you decide to go with interval notation, I'm also happy. So I mean, you decide based on your taste. Okay. All right. Oh, that's something from before. Let me erase it. Okay, so the final thing the final thing in this review section is about solving this quadratic equation. This is a consequence of quadratic formula. By the way, if you forget about quadratic formula and you would like to have a refresher, or if you want to have it in great details, I have a I have a video on my channel. Just go to my channel and just type in the quadratic formula. There's, I think it's like a 2-hour thing, but you can obviously skip a lot of steps and go immediately to the application, because we proved in that video, I remember we proved the actual formula. So if you don't care about the proof, just jump into some exercises, refresh, see the formula, and you're good to go. This is a consequence of it. I'm just recalling it. So it goes like this. If you have a number that's labeled as b that's non-negative, the following equivalence holds. A squared equals b if and only if a is plus or minus square root of b. Okay. For example, if x squared is equal to, I don't know, 9, right? So if x squared is equal to 9, who's a, who's b? A is x, b is 9, right? According to this, that means x is minus square root of b, which is 9, or x is plus square root of b, which is 9. Okay, one more time. The x is the a, and the 9 is the b. Correct? I mean, just direct comparison allows you to see that the a is x and the b is 9. So to transition to linear power for a, if you don't want the 2 anymore, if you want just 1 power 1, so like here I need just the x, what you do is you take plus or minus the square root of the guy b. Okay, so you get x is minus square root of 9, or x equals plus square root of 9. And this is easy, this is minus 3 and this is plus 3, right? So x is plus or minus 3. So these are the only two guys you plug in for x, you square them, you get 9, right? So this is intuitive actually, but this guarantees that there are no more guys. All right. Okay, so let's erase all of this and let's go to the next problem. Solve each equation. Part 1. So part 1, x2 plus 1 is equal to 6. Well, this is very close to the one we just discussed. The only difference is I have a plus 1 here. Well, I can get rid of the plus 1 in order to put myself in this context, right? In order to put myself in this context, what do I need? I need the right side, one of the sides, the left side to be a perfect square and the right side to be non-negative, right? Okay, so that's equivalent to x squared equals 5. Am I correct? By just chipping one unit from both sides. So x2 plus 1 minus 1, you lose them 1, and 6 minus 1 is 5. You get this. Now you are in the context of a squared equals b. So I'm gonna use this part. I'm gonna use this part to get what? Who's a, who's b? So let's be very clear. So use the result above with a, capital A. Who's capital A here? Who's the capital A here? It's the x. And the capital B to be 5, right? So I'm telling you what I'm using. I'm using this, I'm telling you what the ingredients are. The a is x, the a in the formula is the current x, and the b in the formula is the current 5. Certainly my b is non-negative, right? Certainly my b is non-negative. As such, I can apply this formula and get what? And get that the a, which is the x, right? The a is minus square root of 5, or the x is plus square root of 5. Correct? So you get exactly that one. So solve each equation. I solved it. The only solutions are minus square root of 5 and plus square root of 5. Okay. All right. Part 2. 4 times the square of x minus 3 is equal to 28. Well, I don't see yet that I have this setup. I see a square, but I have a 4. Well, there are multiple ways to finish this. Let's finish it in the most natural way. How about we divide both sides by 4? If we divide both sides by 4, we get x minus 3 squared is equal to 28 over 4, and 28 over 4 is simply 7, right? 28 over 4 is simply 7. We get this. So this whole thing is equivalent to this by dividing both sides by 4. If you divide by 4, you're undoing the action of multiplying by 4, which means this is gone, and 28 divided by 4 is 7. Alright, now I have this set up. So now I have this set up. So I'm gonna apply now the earlier result, this result. So apply the result above with the a to be, who's the a now? Who's the guy that's squared? It's the x minus 3 that's squared, right? I'm squaring x minus 3. So a is x minus 3, and the b is the 7, which is certainly greater than or equal to 0. So it fits this condition, right? Okay, and we obtain that a is plus or minus square root of b. So the a, which is x minus 3, is plus or minus square root of 7, because the b is 7. So minus square root of 7, or the x minus 3 is plus square root of 7. Okay, and then what is x then? So this means that x is, if you just add 3 to both sides, you get 3 minus square root of 7 for the first one, or x is 3 plus square root of 7 for the second one. Correct? For this one, if you add 3, this side becomes x, this side becomes minus square root of 7 plus 3. Minus square root of 7 plus 3 is 3 minus square root of 7. Same thing. And similarly here, if you add 3, you get x, and if you add 3, you get square root of 7 plus 3, and square root of 7 plus 3 is 3 plus square root of 7. So still we get this one. Alright, so this completes this section.